Check the sound. That looks good. All right. So today we're going to review for Exam 2, Chapters 4, 5, and 6. And this is CH203. So I'll open the floor first to see if you've got any specifics that are bothering you. See, I didn't mark these, the ones that I had assigned. And this should be this. Okay. Oh, it must be in Blackboard. Or a second. I think I had a separate handout for that. Let's see where it is. Well, that's strange. Oh, let's put it. It's in the front. Let's put it. There you go. So these are the problems that I assigned for you to give you practice enough to pass an exam. Quite a few of them. All right. So is there any one thing that's giving you trouble?
I forgot one or few questions at the house, but I think the majority of like my problem was in chapter 5. Those questions.
Chapter 5?
Yeah.
Okay. Chapter 4 is the ionic bond model. Chapter 5 is the covalent. Oh, we had naming compounds too, didn't we? Are you having any trouble with that?
A little bit, but not.
You know when to apply type 1, type 2, and type 3?
Okay, sure.
You want to review that?
Yes.
Okay. So, the naming convention for binary compounds can be divided into 3 types. Type 2 and type 3. Okay. Type 1s and type 2s are pure ionic compounds. That is, both the cation and the anion are specified in this order. Cation first, anion second. The cation is simply named by the compound. I mean by the element, excuse me. For instance, potassium would be K, and the anion would be, for example, chlorine. So this has a +1 charge, that has a -1 charge based on its position in the periodic table. Potassium is in the alkali metals, they're always +1. Chlorine is a halogen, it's always -1. Okay, so when you name a type 1 compound, since their charges are fixed, you don't have to say anything about their charges or how many there are. You just say potassium for the cation, and then the chlorine becomes chloride. And that's it. That's all you have to say. Another example. How about magnesium? And we're going to combine it with an anion, and these are always metal, non-metal. Same for both. Metal's the cation, non-metal's the anion. Okay, we were on magnesium. Let's combine magnesium with fluorine. Right? Okay. So magnesium is an alkaline earth in the second column, which means it always has a 2+ charge. Fluorine is another halogen, so it always has a -1 charge. So in order to make them balance, you need 2 fluorines to give you 2 negatives against 2 positives for magnesium. Okay. Then we just say magnesium chloride. And we got our compound name. Okay. The other possibility is one or both of the components of the binary might be polyatomic. So that's why I gave you that handout with all the polyatomic ions on it. For instance, well, I'll just do one where both of them are polyatomic. The only cation in the polyatomic chart is ammonium. Okay, it's NH4, and it has a +1 charge. All the polyatomics have a single charge, never changes. So that means they fit into this category. And then we're going to combine it with nitrate. Okay, so that's NO3, and it has a -1 charge. So since ammonium has +1, nitrate has -1, you just need one of each, and you're balanced. The polyatomic ions, their names are fixed, so you don't have to do any changes. The ammonium ion is this, the nitrate ion is that, you just put them together. Okay, that's type 1. Type 2 is also metal, non-metal. The difference being that the cation, or the metal, could possibly have more than one charge. I mean, in the compound, it'll only have one charge, but you have several charges to choose from in constructing the binary. So, and most of those come from the transition metals. That first transition metal in the group is scandium, and it runs across to zinc. And then yttrium is in the next period, runs to cadmium, and then lanthanum runs across to mercury. Those are, we're going to assume that all the transition metals could possibly have multiple charges. There are a couple that don't. So for those, I'll accept either naming it like this or naming it like this. One is silver, and the other is zinc. Silver is always a +1 charge, zinc is always a +2 charge. But in order to keep things from getting too complicated, if it's a transition metal, you can use the type 2 convention. There are some other metals in the representative groups, like lead. Lead could be +2, it could be +4. So when you have multiple possible charges for your metal, you have to say in the name what the charge is. That's the only difference between these two. So let's take lead then. So let's say we have lead, and we combine it with, and say it's a +4 charge. And we combine it with, let's take a polyatomic, like nitrate. Right? So how many nitrates will it take to balance the 4+? Take 4 of them. So we would say, remember the polyatomics cannot be messed with. You can't change the subscripts of a polyatomic. So in order to get more of 2 or more of them, you have to use parentheses. So now it's balanced. We've got 4 negatives, 4 positives. Now we have to name it. So we just say lead, and then what's the charge on lead? Well, we use a Roman numeral to give you the charge. Lead 4, and then the anion. Okay? Let's try another one. Say iron and oxygen. Okay? Where does oxygen come from? We're going to start with the anion. Oxygen comes from the 1 to the left of the halogens. So the halogens are -1, oxygen's -2. Okay? So it's going to be 2 minus always. But the iron could be +2, +3. So we're going to say, we're going to make the iron +3 charge. Okay. Now we need to balance the charges. When you have an odd and an even charge to balance, the best way is to cross multiply. Just bring the 2 over here and the 3 over here. And then you can check yourself. 3 times 2 minus and 2 times 3 plus. You're balanced. So Fe2O3 is the correct formula. Now we need to name it. So we just say iron, 3 for the charge, and then oxide for the anion. Okay? So that's your type 2 compound. The only difference between this one and this one is the possibility of more than one charge for the cation. Type 3s, we have this type of arrangement, but it's not real because type 3 compounds are not ionic, right? But we build off of this convention of type 1s, type 2s to construct our type 3 compounds. And the combination is going to be nonmetal with nonmetal. Right? So they're always going to come from the right-hand side of the chart. Suppose we have this compound. We could say that oxygen has a 2 minus charge, but in this case, it doesn't have a charge because these are ionic compounds. These are all covalently bound compounds. And when you name the type 3s, since we don't have a charge to work from, you just say how many of each one, building on this structure. So we would start with carbon, and then oxide for the oxygen. Then we have to say how many of the oxygens there are, and we use the Greek prefix for 2, which is di. And that's our name, carbon dioxide. We never say mono for the cation equivalent for this one. We don't say it. If there's only one of them, you just say the name. You only say mono if you're back here in the anion side. So if we had this compound, it would be carbon monoxide. Okay? How about, let me write the name, and let's figure out how to go the other direction, write the compound. So if we have, how about this one? Diphosphorus pentoxide. How would we write that? Well, we know that phosphorus is that position, and oxygen is that position. Then we just look at the compounds. It tells us how many of each one. So diphosphorus means 2, and pentoxide means 5. Okay? Type 1, type 2, type 3. Let me think. Do I have any examples of a type 3 with polyatomics? Can't think of any. Did we do that extra credit for naming compounds yet? That should be for this group. So if you turn in, let's see, where is it? Here. This one, you get a copy of this one. Yeah, that's extra credit. It gives you a practice naming compounds. Okay. We did, let's see, did we do, I'm looking to see. Okay. The last exam had electronic configurations, but we want to build on electronic configurations into the periodic table thing. Let's see. No, we're just doing bonding models. Okay. Oh, we are going to get to Lewis dot structures, right? That was part of this group of chapters. Okay. So any questions? So I can erase this. Okay. Let's see it. Okay, that's coming through all right. Some of these colors don't show up very well. Check. All right. Let that one rest and see if this one works. Lewis dot structures. Okay, the purpose behind the Lewis dot structure is to help with forming chemical bonds and accounting for all of the valence electrons that are in the, well, valence electrons are in the outer shell of each of the elements that are in the compound. So we start off with drawing the Lewis dot structure just for individual atoms, and then we use that knowledge to build our molecules. For instance, a Lewis dot structure is going to have an element symbol, and it's going to have so many dots representing electrons around it, and the maximum is 8. So you can have 2 here, 2 here, 2 there, 2 there. So how do you know how many? Well, you identify how many on the periodic table. If your, I have a pointer. If your element comes from the alkali metals, you're only going to have 1 dot. So the left hand first group. Second group will have 2 dots. Third group, and we skip the transition metals. Third group is boron, aluminum in that group. They will have 3 dots. The next carbon group will have 4 dots. Nitrogen group will have 5 dots. Oxygen will have 6. Fluorine and its neighbors in that group, the halogens, will have 7 dots. And then all of the noble gases will have 8 dots. That's why they don't bond, because there's no drive to complete the 8-dot complement around the element. Okay? So if we take magnesium, comes from the second group, it's going to have 2 valence electrons. That's it. Now that's magnesium when it's neutral. Right? Magnesium that's charged will have none. Right? Because if we take 2 negatives away, that leaves 2 positives behind, 2 protons. That's why this is 2 plus, and that's neutral. See? Because we took those 2 valence electrons away. If we look at the other side, say oxygen, oxygen's going to have 6 valence electrons. So we just start here and go around. 2, 3, 4. Then you can start pairing. 5, 6. Okay? Now, think of it this way. Everybody's trying to look like a noble gas. They're trying to have a complete octet, 8 electrons in their valence shell. If they can get it, fine, they're perfectly happy. If we combine oxygen with magnesium, it's easier for magnesium to get rid of those 2. Because what happens? When magnesium gets rid of 2 electrons, it's walking backwards towards sodium and then neon. So now it looks like neon in its outermost shell. We don't show it here, but now it has a complete outer shell like neon if it loses 2 electrons. That's easier than gaining 6 more electrons to look like argon. But when you're over here on the right-hand side in the nonmetals and you're close to the noble gases, it's easier to add the electrons that you need to complete your shell. So oxygen will want to add 2 electrons, and that gives it a 2- charge because we've added 2 electrons. That's why oxygen and all its in that group are 2- charged. When we talked about the compounds earlier, naming the compounds. So, when magnesium and oxygen come in contact with one another, if they start off with these structures, then what happens is this electron transfers over here, this one transfers over here. Magnesium's happy because it got rid of those 2 electrons it didn't want. Oxygen's happy because it got 2 electrons that it needs. And now we have magnesium, one electron from oxygen, 1 electron from magnesium, another electron from magnesium, and another from oxygen. No, that's not right. That's right. Now oxygen thinks it has 8. 2, 4, 6, 8. Because these are in the bond. And magnesium is perfectly happy to let oxygen have them. So now magnesium looks like neon in its electronic structure, and oxygen looks like neon in its electronic structure. Okay. Of course, this implies that they're sharing the electrons, but they're not. What actually happens is, we're like this is a 2- charge, this is a 2+ charge, and the attraction is electrostatic. So that's the ionic compound, the ionic bond, when you completely separate the charges. But if we have a type 3 compound, where you have 2 nonmetals, then you're going to get sharing of electrons. So for the carbon dioxide, we're going to have carbon is going to have 4 electrons to start with. Oxygen is going to have 6. Okay, on both sides. So we have 2 of them. 6 there, 6 there, and 4 here. Now what happens is, in order to complete their octets, they're going to share. So oxygen is going to share that one, and that one. And this oxygen is going to share, let's see, this one, and this one. Okay? So now, if you ask oxygen how many electrons it has in its outer shell, it's going to say 8. 2, 4, 6, 8. If you ask carbon how many it has, it's going to say 2, 4, 6, 8. And that one's going to say 2, 4, 6, 8. So sharing makes them think they have a complete octet. And then the way we write that, if we use only dots, it would be like that. And to be sure, count up dots: 2, 4, 6, 8, 10, 12, 14, 16. 16 electrons. Well, let's see. Did we start off with 16? Well, we have 6 on this side. 6 on that side is 12. Plus 4 for carbon is 16. So we didn't create any, we didn't destroy any. Now, typically how we write this is like that. And sometimes we put the electrons in here like that. But that means the same thing. Each one of these lines is 2 electrons in the bottom. Now we can use Lewis dot structures to draw more complex molecules. For instance, let's see if I can think of a good one. Let me see if they can give me an example so I don't have to rack my brain. Lewis dot structure. We'll probably covalent model right there. Okay, that would be all right. What if we do this one? The sulfate polyatomic ion. All the polyatomic ions are covalently bound, and they share that their charges, whatever they might be, over the entire molecule. So if we want to draw the Lewis dot structure for this molecule, there are certain steps that you go through. First, you look at each of the elements, find out how many valence electrons are assigned to that element. Sulfur and oxygen are in the same family, So they're both going to have 6 electrons. Right? So you have 6 electrons for sulfur, and then you have 4 times 6 for oxygen. And then you have 2 for that charge. Right? Don't forget the charge. So this would be 32 electrons that have to be placed in that molecule. Okay? Now you start off by building the molecule. We have 4 oxygens attached to that sulfur. And I draw it this way because it's cleaner rather than putting dots in here. So each one of these is 2 electrons. That means we've used 2, 4, 6, 8. So that would be 24 electrons left over that we have to place. Now you start from the outside and work your way in. So we want to place 24 electrons. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So we've used them all up. Okay? But we also have to preserve the charge. Right? So for this entire molecule, we have 2 minus charge. Okay? That's the Lewis dot structure for the sulfate polyatomic ion. Let's see. We'll do one more. Okay. Let's try. Earlier we named diphosphorus pentoxide. So let's see if we can work that one in. So diphosphorus pentoxide. Okay, phosphorus is in nitrogen's group, so it's going to have 5 valence electrons. So we have 2 times 5 for phosphorus, and then we have 5 times 6 for oxygen. So that's 40 electrons. Right? 30 plus 10 is 40. Now we're going to have phosphorus is going to be bound to another phosphorus. And then the oxygens are going to be placed around them. 1, 2, 3, 4. And then you just choose which side to put the other oxygen on. Okay, so that's 2, 4, 6, 8, 10, 12. So we have 28 electrons left over. Now we start placing the electrons out here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Wait a minute. Let's see, I had 28. 2, 4, 6, 8, 10, 12, 28. So I got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 25, 26, 27, 28. So these two are short electrons. Plus, you try to complete the octet, right? For this one, sulfur has 2, 4, 6, 8. That's an octet. Each of the oxygens has 2, 4, 6, 8. That's octet. For this one, this phosphorus has an octet. That phosphorus does not. So, what are we left with? Well, if we take this electron and combine it with, well, that's not going to work. So I'm sort of painting myself into a corner here. I think I've positioned the electrons incorrectly. That's the problem. Let's try that again. Sometimes you have to forego the possibility of a perfect octet. It's just the way it is. So with 28, let me start this again. 1, 2, 3, 4, 5. Wait a minute. I built this molecule incorrectly. It's got an oxygen in the middle, phosphorus on the outside. 5. 1, 2, 3, 4, 5. That's the problem. Oxygen's in the middle. Okay. 2, 4, 6, 8, 10, 12. Still got 12 here. So now we can start placing the electrons, and it should work out. The clue there was that I couldn't get an octet with that other arrangement. 1, 2, 3. No, this is in the center. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 4. Okay, now we have octets for all the oxygens with 24. We have 4 electrons left. Now we work our way in with 4 electrons. So 1, 2, 3, 4. Okay. Now we have all the electrons positioned, but we don't have octets, right? Everybody's got an octet except this guy right here. So here's what happens. These two make a bond, and these two make a bond. So it goes like that, and they're gone from that position. So now we still have 2, 4, 6, 8 around the phosphorus. 2, 4, 6, 8, and then we have 2, 4, 6, 8. Okay? So that's a valid Lewis dot structure. And I say valid because just because you write one structure doesn't mean it's the only one. But in this case, it works when we do it that way. So we erase those because they've been used in a bond. Okay? Let's see if I can show you, oh, I know one, where we don't get an octet. This one is a valid compound. It has been identified, characterized, it's real. So we have to deal with what we've got. So boron comes from the group with aluminum. It has 3 valence electrons. And then fluorine has 7 each. Right? So we have 3 plus 21 is 24. Okay? So this one, I know boron's in the middle. So fluorine, fluorine, fluorine. 2, 4, 6 means we have 18 electrons left over. Okay? So we start placing them around the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, all of our electrons are placed. And boron doesn't have an octet. All the fluorines have an octet, but boron doesn't. It's deficient. And I guess we could say, well, why doesn't one of the fluorines donate, to a double bond with boron? I guess that's possible. But it's not true. How do I know that? I read it somewhere. We have other possibilities where you exceed the octet. I'm not sure if they show you any of those in here. Some of the ones where you exceed the octet are forced compounds that are made with noble gases. Such as xenon hexafluoride, I think is a real compound. Okay, so xenon's already got 8. Fluorine's got 6 times 7 is 42, so that's 50. So we put xenon in the middle, and then we have 1, 2, 3, 4, 5, 6 fluorines. Okay, so that's 2, 4, 6, 8, 10, 12. We need 38 electrons. So if we put 1, 2, 3, 4, 5, 6 around each of the fluorines, six times 6 is 36. So we have 2 electrons left over. But we're not going to exceed the octet on a fluorine. But we can exceed the octet on a xenon because it's a much, much larger atom. It will. Plus, okay, let me go ahead and put them in here. So the xenon is going to exceed that by a lot, actually. 2, 4, 6, 8, 10, 12, 14. So xenon has 14 electrons in that outer shell. Actually, what happens, see xenon, but let's start with fluorine. Fluorine here, remember, it's using N equals 2. So it's got 2s and 2p to fill up electrons. But xenon has access to s, p's, and d's. So it uses those d orbitals to accommodate the extra electrons. That's why we can form a compound with it and it can exceed the octet. Because the octet is based on the theory that you have 2 electrons maximum in the s orbital and 6 electrons maximum in the p orbital. So it could be a 2, a 3, a 4, whatever. Principal quantum number here. That's where the concept of the octet comes from. But when you're dealing with those elements that have access to a d orbital, then they can accommodate more. 2, 4, 6, 8, 10, 12, 14. So 8 from 14 is 6, right? So that's where those other 6 go. They're accommodated by the d orbital. Okay.
Let's see. Did we do? We've already done the SEPR model, haven't we? We do the structures. Oh, maybe it is in this chapter. Let's see. Let me look back. Let's see. We have trigonal planar. Yeah, it's in this group. Okay, so once you get your compound correctly written, then we can say something about its structure. And the reason we want to know structure is because that informs us about the polarity of the molecule. So for instance, say we have the ammonia molecule. Okay? So nitrogen, let's draw the Lewis dot structure. Nitrogen has 5 and 3, 1 for each for the hydrogen. So that means we have 8 electrons. Okay, so nitrogen, like that, 2, 4, 6. So we have 2 electrons left over, and hydrogen doesn't accommodate anymore, right? It only satisfies a duet because it's only got 1 proton. So we put the other 2 electrons right here. Okay, now we have a valid Lewis dot structure, and then we go back to the number of electrons, then the electronic geometry, and then the molecular geometry. Let me move this over. Okay, so the number of electrons that are around the central atom, and we don't say, it's actually not the number of electrons, it's the number of electron groups. Because if we have double bonds, we count that as 1 group, right? So the number of electron groups we have here is 1, 2, 3, 4. Right? So we have 4 electron groups. And the electronic geometry for arrangement of 4 groups is tetrahedral. What they're trying to do is get as far away from each other as they can. That means a regular geometric structure that maximizes the distance of all the electrons to one another. And this one means tetrahedral. Then to find out what the molecular geometry is, you just cover up those lone pairs. Right? So if you've got a tetrahedron here with nitrogen in the middle, and like that, right, with your tetrahedron, then when you cover this one up, what does that mean for the geometry of the molecule? Well, then it becomes a trigonal pyramid, because the molecular geometry discounts all the lone pairs. So the actual molecular structure is the trigonal pyramid in that case. And this is if you have lone pairs. One lone pair. If you have this one and no lone pairs, it's still tetrahedral. So what's an example of that one? A good example of that one is methane, CH4. There are no lone pairs. So the electronic geometry is the same as the molecular geometry. Okay? Now, the groups here, you can have, if you have one electron group, say this one's bound to just one other one, it's always linear. If you have two groups, they're also going to be linear. And if one of them happens to be a lone pair, you're still linear because you've only covered up one side of the molecule. So these are going to be linear. But if you have three, what's the electronic geometry for three groups is trigonal planar. Okay? Now, it depends on how many lone pairs you have as to whether some other influence. So if you have trigonal planar with, say, something out here, but you have a lone pair there, then what does that give you? That gives you an angular or bent molecule. Okay? If you have this one, and you have two lone pairs, then that also gives you a bent molecule, right? Because if we replace one of these, let's make it a real molecule. Like, let's do this. Put the hydrogen here, put the lone pair down there. So now if you cover up the lone pairs, you get a bent molecule. That's water. So you can see it gets a little complicated. It just depends on how many lone pairs you have. The electronic geometry is fixed for the number of groups you have. So if we have 5 groups, then we have a trigonal bipyramid. So it has 3 around the center and then 1 each up top. So that's 3 plus 2 is 5. And then if you have 6, this is octahedral. Okay. So your book includes discussions, and I also included some things in the PowerPoints that I thought were a better representation of the information than was given in the book. Okay, are we into chapter 5 yet? That's chapter 5. That's the one that was giving you trouble? Okay. All right. Now I'm not going to give you really hard ones because it takes a lot of practice to get comfortable with this stuff. So I just want you to know the basics, how to deal with, how to make a Lewis dot structure, how to determine what its electronic structure is, and then its molecular structure. A very simple compound. Then we got into a discussion of electronegativity and polarity of bonds. Okay, so once you know what the structure is, you look, 2 things determine the polarity of a molecule. Right? One, let's see, polarity of the molecule. 1, polarity of individual bonds in the molecule. And 2, the molecular structure. Of the molecule. Those 2 go together to determine the polarity of the molecule. Okay? So if we have, say, let's go back to methane. If we have methane, it's going to be with 4, it's going to be octahedral, right? In structure, and these are all regular arrangements. Now, the polarity of the bond between carbon and hydrogen, it's not that polar, I don't think. Did I give you a chart with the electronegativities? Here we go. Carbon is a little more electronegative than hydrogen, just a little bit. It's like a difference of 0.4. So we do get a slight polarity of the bond for each one toward carbon. Not much, just a little bit. Right. So let's see, what was the rule? I saw the chart. The rule on bond polarity, here it is. 0.4. 0.4 or less is nonpolar. So that's considered a nonpolar covalent bond. But even if it was polar, it wouldn't matter because the geometry is regular. It's a tetrahedron, and all of these vectors on the bond cancel one another out. So overall, this is a nonpolar molecule. Okay? Let's do another one with carbon. Now this one is definitely polar bond toward the oxygen. Oxygen is more electronegative than carbon. So these bonds are going to be polar. But it's a linear molecule, right? 2 groups around the central atom, 2 means linear. So the polarity of each bond is identical but opposite. They cancel one another out. So that means the molecule is nonpolar. How about this one? The ammonia. Okay, let's see, hydrogen and nitrogen. What's the difference there? I'm looking in my PowerPoints. I got a little chart in there. Wait a minute. I don't need the chart yet. What I need is the table. Here it is. Hydrogen's 2.1, nitrogen's 3. So that's a difference of 0.8, 0.9. The 0.9 difference should be polar covalent. Yeah. So these bonds are polar toward nitrogen. Right? And there is a polarity, of course, for the whole molecule that's devoted to that lone pair. Because it's negative, just sitting out there negative, not balanced by anything. So a combination of these guys, this is a non-symmetrical molecule for these bonds. So they add together along with that lone pair to make a polar molecule. Okay? So we got the polarity of the bonds and the molecular structure gives us a polar molecule. Same thing with water, because it's bent. So you got polarity this way. Yeah. And that arrow, I think I told you what that was. That's the dipole moment for the bond. Right? Plus, it's got two lone pairs up here. So overall, the water molecule is polar toward oxygen. So what does that mean? That means that this side of the molecule is slightly negative, and this side of the molecule is slightly positive. So when they're together in liquid state, they're pure, they orient one another so that this side becomes attracted to that side on another molecule. And that adds to the strength, the intermolecular forces that hold water together. That's why water is a liquid at these temperatures and pressures and not a gas. Right? For a nonpolar molecule at these temperatures and pressures, carbon dioxide is a gas because it's nonpolar. And water freezes at 0 degrees centigrade, and carbon dioxide becomes a solid at minus 78.5 degrees. So it has to get a lot colder for it to not be a gas anymore. Okay, now, specific questions in chapter 5. I don't want to just ramble on, I want to answer your questions.
But I probably have to head out kind of early because Mom keeps messaging me telling me that the roads are getting worse.
Oh,
Would it be okay?
yeah, that means we won't even have lab, right? Okay.
I'm sorry. I'm sorry.
Okay, as long as we cover all the topics. So, let's see, chapter 5, chapter 6, calculations. All right, so can you determine the molar mass of a compound?
Isn't that where, I have to look for this.
For example, let's just, let's say, how about, yeah, that was pooping out on me. That one is due. Okay, how about this one? There. Sodium sulfate, right? We know this is right because that's a 2 minus and this is 1 plus, so you need 2 of those, like that. So now that we have the compound, how do you determine the molar mass of that compound? It's just the sum of the molar masses of all of the elements. Right? So sodium is, what, 23, I think? Yeah, 23. Sulfur is 3206. Sulfur is 3206, and we only have 1 of them, but we have 4 oxygens. Okay? So just add those up, and that'll give you the molar mass of that molecule. And these are in terms of grams per mole. Okay? So it's the same units for the individual atoms and for the compound. Now, some instances in there, if we're talking about a mole of sodium atoms, or 1 mole of that compound, then it's grams per mole. If we're talking about 1 molecule, then these values will be atomic mass units. Okay? But their magnitude is exactly the same. It's just the units are different. Now, the more practical one that we use is the grams per mole. Let's see. Balancing equations. Did anything in balancing equations stump you? You doing good with those? Okay. Like, does that budgeting system help?
Yes, that helps a lot.
Okay. So we got that covered. Let's see. Stoichiometric calculations. So once you've balanced your equation, you can use it, let's see, methane and oxygen. Do that. Oxygen. I think there are two of them. Carbon dioxide and water. So it's four hydrogens, 4 oxygens, 1 carbon. There, that's balanced. Okay, what does that tell you? A balanced equation tells you what's going on in the microscopic world. 1 molecule of methane combines with 2 molecules of oxygen to make 1 molecule of carbon dioxide and 2 molecules of water. Okay? At the macroscopic level. But if we say, okay, I can't deal with that. My balance won't weigh individual molecules. It has to have a lot of them. So 1 mole, 6.022 times 10 to the 23rd molecules of methane combines with 2 moles of oxygen to make 1 mole of carbon dioxide and 2 moles of water. That's the way we use it most often. So what that means is, if you have a mass of methane over here, say, I don't know, 10 grams, then you can use this formula to tell you, well, how much carbon dioxide will that produce? You know, how many grams of carbon dioxide? The trick is, though, that this is not in terms of grams, this is in terms of moles. So you got to convert that to moles first. Right? That's why I hammered conversion factors so hard at the beginning. Right? Cancel the grams and leaves you with moles. So you need to know the molar mass of methane. So that's 12.01, and 4 hydrogens is 4.04, which is 561 grams per mole. So 16.05 gives us, my calculator. How soon do you need to?
Like in a few minutes.
Okay. I just want to be sure that I think this is the last topic, except for percent yield, and percent yield is just a formula. But, yeah. So now, 10 divided by 16.05 gives us 0.623 moles of methane. Now, if we want to know how much CO2, we can now go from here to here. See, there's a great wall in here. There's several great walls. You can't cross that wall unless you're moles. If your mass, if your concentration in a solution, doesn't work. It's got to be moles. So now we need a conversion factor that will take us to CO2 from methane. Right? You construct that conversion factor from the coefficients. Turns out it's 1 to 1. One of these for one of those. So we have 623 moles of CO2. Now we can convert back to mass. We just need the molar mass of carbon dioxide. So we need 12.01, and then 2 oxygens is 32. So that's 44.01 in our conversion factor. In this case, I put grams on top, moles on the bottom, because I'm canceling moles. So 44.01 times, and that means we produce 27.4 grams of CO2. And there's your answer. That's stoichiometry. All right. Well, I don't know what I'm gonna do about the lab since nobody showed up. We'll see. It was a fun one. I might just have to cancel it. Okay, so contact other people in your class and try to get that other one in. Because I have to turn in grades on the 11th. So if you can send it to me in an email or upload it on Blackboard, then I can incorporate that grade. Otherwise, all missing grades I have to count as 0. Of course, at the end of the semester, if you've turned it in by then, of course, it will go into your calculation, but I don't know, they may not be happy about a low grade midterm, especially if you're getting financial aid. Okay, so I guess we'll shut this off and wait for the next class. Be safe.